Okay, let's continue. Some important questions. Although for the differential equations 15 and 17, this 15 and 17, we are able to verify that certain simple functions are solutions. In general, we do not have such solutions readily available. Thus, a fundamental question is the following. Does an equation of the form A, this form, always have a solution? The answer is no. Merely writing down an equation of the form A does not necessarily mean that there is a function y equal to phi of t that satisfies it. So how can we tell whether some particular equation has a solution? This is the question of existence of a solution, and it is answered by theorems stating that under certain restrictions on the function f in equation 8, the equation always has solutions. This is not a purely theoretical concern for at least two reasons. If a problem has no solution, we would prefer to know that fact before investing time and effort in a vain attempt to solve the problem. Further, if a sensible physical problem is modeled mathematically as a differential equation, then the equation should have a solution. If it does not, then presumably there is something wrong with the formulation. In this sense, an engineer or scientist has some check on the validity of the mathematical model. If we assume that a given differential equation has at least one solution, then we may need to consider how many solutions it has and what additional conditions must be specified to single out a particular solution. This is the question of uniqueness in general. Solutions of differential equations contain one or more arbitrary constants of integration, as does the solution 16 of equation 15. 16, 15. Because this is a small c, it can be arbitrary constant. Equation 16 represents an infinity of functions corresponding to the infinity of possible choices of the constant small c, as we saw in section 1.2. If p is specified at some time t, this condition will determine a specific value for c. Even so, we have not yet ruled out the possibility that there may be other solutions of equation 15 that also have the prescribed value of p at the prescribed time t. As in the question of existence of solutions, the issue of uniqueness has practical as well as theoretical implications. If we are fortunate enough to find a solution of a given problem, and if we know that the problem has a unique solution, then we can be sure that we have completely solved the problem. If there may be other solutions, then perhaps we should continue to search for them. A third important question is, given a differential equation of the form 8, this form, can we actually determine a solution? And if so, how? Note that if we find a solution of the given equation, we have at the same time answered the question of the existence of a solution. However, without knowledge of existence knowledge, we might, for example, use a computer to find a numerical approximation to a solution that does not exist. On the other hand, even though we may know that a solution exists, it may be that the solution is not expressible in terms of the usual elementary functions, that is, polynomial, trigonometric, exponential, logarithmic, and hyperbolic functions. Unfortunately, this is the situation for most differential equations. Thus, we discuss both elementary methods that can be used to obtain exact solutions of certain relatively simple problems, and also methods of a more general nature that can be used to find approximations to solutions of more difficult problems. Technology used in differential equations. Technology provides many extremely valuable tools for the study of differential equations. For many years, computers have been used to execute numerical algorithms, such as those described in Chapter 8, to construct numerical approximations to solutions of differential equations. These algorithms have been refined to an extremely high level of generality and efficiency. A few lines of computer code written in a high-level programming language and executed, often within a few seconds, on a relatively inexpensive computer suffice to approximate to a high degree of accuracy the solutions of a wide range of differential equations. More sophisticated routines are also readily available. These routines combine the ability to handle very large and complicated systems with numerous diagnostic features that alert the user to possible problems as they are encountered. The usual output from a numerical algorithm is a table of numbers listing selected values of the independent variable and the corresponding values of the dependent variable. With appropriate software, it is easy to display the solution of a differential equation graphically, whether the solution has been obtained numerically or as a result of an analytical procedure of some kind. Such a graphical display is often much more illuminating and helpful in understanding and interpreting the solution of a differential equation than a table of numbers or a complicated analytical formula. There are on the market several well-crafted and relatively inexpensive special-purpose software packages for the graphical investigation of differential equations. The increased power and sophistication of modern smartphones, tablets, and other mobile devices have brought powerful computational and graphical capability within the reach of individual students. You should consider, in the light of your own circumstances, how best to take advantage of the available computing resources. You will surely find it enlightening to do so. Another aspect of computer use that is very relevant to the study of differential equations is the availability of extremely powerful and general software packages that can perform a wide variety of mathematical operations. Among these are Maple, Mathematica, and MATLAB, each of which can be used on various kinds of personal computers or workstations. All three of these packages can execute extensive numerical computations and have versatile graphical facilities. Maple and Mathematica also have very extensive analytical capabilities. For example, they can perform the analytical steps involved in solving many differential equations, often in response to a single command. Anyone who expects to deal with differential equations in more than a superficial way should become familiar with at least one of these products and explore the ways in which it can be used. For you, the student, these computing resources have an effect on how you should study differential equations. To become confident in using differential equations, it is essential to understand how the solution methods work, and this understanding is achieved in part by working out a sufficient number of examples in detail. However, eventually, you should plan to utilize appropriate computational tools to complete as many as possible of the routine, often repetitive, details, while you focus on the proper formulation of a problem and on the interpretation of the solution. Our viewpoint is that you should always try to use the best methods and tools available for each task. In particular, you should strive to combine numerical, graphical, and analytical methods so as to attain maximum understanding of the behavior of the solution and of the underlying process that the problem models. You should also remember that some tasks can best be done with pencil and paper, while others require the use of some sort of computational technology. Good judgment is often needed in selecting an effective combination.